You clicked on this video because you saw news about LimX Luna and want to know if it is real hardware or just marketing hype. The stakes are high because investing in unproven robotics can drain budgets without delivering the autonomy your facility needs. By the end of this analysis, you will understand exactly how to distinguish between a functional industrial partner and a conceptual software demo that cannot move heavy loads. The conversation around LimX Dynamics often centers on their verified platforms like the OLI quadruped and the CL1 humanoid robot. These machines have demonstrated actual loco-manipulation capabilities in open-source repositories using simulation frameworks such as MuJoCo and Isaac Lab. That work proves they possess the software infrastructure required for embodied AI, which is a non-negotiable foundation for any serious robotics company. However, when you search specifically for a machine labeled LimX Luna, described as a next-generation full-size interactive humanoid robot, the evidence evaporates into thin air. There are no physical hardware specifications available in their technical documentation, no power density metrics to verify battery life or thermal management strategies, and absolutely no benchmark data showing how this unit performs under load in an unstructured environment. This discrepancy is not a minor oversight. It represents a fundamental gap between what the company has built and what might be circulating as product news. The confusion likely stems from mixing distinct projects within their ecosystem with a separate entity entirely unrelated to LimX Dynamics engineering. In the broader open-source community, there exists a repository titled LunaXX, which describes itself as meeting your new space best friend through voice-automated software scripts designed for mental health and exercise support. This is purely a Python-based application that runs on standard computing hardware without any mechanical actuators or physical form factor whatsoever. The marketing term interactive in this context has been dangerously conflated with autonomous industrial readiness, creating an illusion of capability where none exists physically. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. To understand why this distinction matters so deeply for your operations, you must look at the engineering trade-offs required to move a full-size, human-sized robot through the real world. A voice automation script can respond instantly because it only processes text and audio signals in memory with negligible power consumption. It does not need to manage momentum or balance against gravity. But when you attempt to replicate that same conversational interface on a physical humanoid platform, every millisecond of processing delay translates into lost stability. The actuator control loops must run at hundreds of hertz just to prevent the robot from falling over while it is listening and speaking simultaneously. This creates a massive computational bottleneck, where thermal management becomes as critical as raw processing speed, because the motors generate significant heat during sustained interaction. Legitimate competitors like LimX Dynamics have demonstrated their maturity through active contributions to simulation frameworks that bridge the gap between virtual testing and physical deployment. Their work on quadruped platforms shows they understand how to transfer policies learned in Isaac Lab into real-world hardware without requiring a complete rewrite of the control stack. This is what we call a simulation-to-reality pipeline, and it requires rigorous validation across thousands of hours of training before a single unit ever leaves the lab. A project limited to voice-automated scripts like LunaXX has no such requirement because there are no mechanical components to fail or wear out during operation. The absence of any verified hardware-software co-design loops for a full-size Luna unit means its industrial viability remains purely theoretical at this stage. Consider the specific metrics that separate a production-ready robot from a prototype script. In established humanoid robotics programs, engineers track power density in watts per kilogram to ensure the battery can sustain operation through a shift without requiring constant recharging or risking thermal throttling during high-torque movements. They also measure actuator reliability cycles to understand how many times an elbow joint can flex before degradation becomes significant enough to impact safety protocols. None of these critical data points exist for LimX Luna because no physical unit has been subjected to such rigorous testing regimes yet. The lack of real-world adoption case studies further isolates this project from the broader industry standard, where companies like Tesla and Figure AI are already deploying fleets with known failure modes and maintenance schedules. The risk here is that your organization might mistake a software demonstration for a complete hardware solution, leading to procurement decisions based on incomplete information. When you see terms like interactive humanoid robot used without accompanying specifications for torque output or battery capacity, treat it as a conceptual placeholder rather than an operational asset. The presence of LimX Dynamics in curated industry lists alongside major players signals that the underlying engineering team is credible and capable. However, crediting them with a product they have not yet substantiated creates a false narrative about their current readiness for full-scale deployment. This confusion between consumer-facing software demos and complex hardware integration loops is exactly where many projects fail to transition from lab curiosity to industrial workhorse. The core insight you need to retain involves the definition of autonomy in an industrial setting. True autonomy requires validated performance in unstructured environments via simulation frameworks that account for sensor noise, mechanical friction, and unpredictable human interaction patterns. A voice assistant running on a server can be autonomous within its digital domain because it does not interact with physical matter directly. But a full-size humanoid must navigate floors, grasp objects of varying weights, and maintain balance while reacting to unexpected obstacles without crashing into infrastructure or personnel. This capability demands validated performance metrics that simply do not exist for the LimX Luna project as currently described in available technical repositories. Until you see published data on power density, thermal management under load, and successful deployment case studies involving full-size operation, treat any claims of industrial readiness with extreme skepticism. The engineering precision required to move a human-sized mass while maintaining conversational fluidity is not achieved through software scripts alone, but requires years of iterative hardware refinement that cannot be faked in an open-source repository or marketing video. The difference between the LimX Dynamics team and purely software-centric projects lies entirely in this proven ability to handle mechanical trade-offs, which remains unproven for Luna despite its conceptual potential. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.